I am fine.
Okay, so we started doing the cylindrical object. We had a wire like this. We wanted to find E. Okay, so you're going to come out here some distance R. We want to find E here. Okay, why would you know to use Gauss's law? Infinite cylinder. Okay. So Gauss's law is always true about where you can only easily apply it. And spherical, infinite plane, infinite cylinder. They're the only times you can easily apply it. So what's the first step with Gauss's law? Yes, draw a Gaussian surface. How are you going to draw your Gaussian surface? Starting right here. So you're going to have this guy here. This has some length here now, like that. Oh, okay. So here's Gauss's law. What's the next step? Okay, how many will we have in this case? Which one?
Because I was supposed to have one at the top.
Okay, so we'll have one at the top. How does the little patch of error go at the top? The vector. Yeah, because the dA vector by the delta A vector by definition is normal and outward. What about on the bottom? Yep. Gonna pick some favorite place on the side. Let's see over here. How does it have to go there? Like this. Now, we draw the electric field. How do we say the electric field goes for a infinitely long wire? If here's a wire like this, it comes out like this. Again, I think the best picture for this is think about cleaning two test tubes. When you use that metal bristle to clean test tubes. It's similar like that's all I did in chemistry for those clean test tubes. When I get the experiment that didn't work, which is entirely my entire year of chemistry. So you have those metal bristles that come out like this. That's what this looks like. So if you draw this, it's kind of this shape here like this. Okay, so we write three terms here, the sum here. Remember, this one you do over the entire surface. We'll have three terms. I have this on the top. This on the bottom. Plus this on the side. What did we say yesterday? Because we started part of this. So tell me about each of those terms.
The area, so the two circles and a rectangle.
What's the dot product?
Oh, the magnitude A.
Okay, so this goes what? This is magnitude of this guy. Magnitude of E. Magnitude of delta A times or dot product cosine of the angle between the two. What angle on the top does the delta A vector make with the electric field? 90. What is the cosine of 90? One of those is correct. Zero. This is 0. So there's no flux through the top. And again, flux tells you how much of a vector pokes out through the surface. This isn't, this electric field isn't poking out through the surface, it's skimming the surface, it's not poking through it. That's why there's no flux through the top. Hey, can we use this argument elsewhere? The bottom, exactly. The same thing happens here. At the bottom here, E is perpendicular to delta A here. So this is also going to be 0. Notice, these terms don't cancel. They're not canceling, they're individually 0. Okay. What about our friend here on the side? So this is sum magnitude of B, magnitude of delta A times the cosine. So if we look right here, right, what is the angle between this E, the E and the delta A here? What angle do they make with each other? 0. What is the cosine of 0? 1. Let's see if you can tell me what's going to happen. What happens here? We have this guy here. We have that the total flux equals this guy here on the side. How do you think is going to happen? What can you say about the magnitude of the electric field anywhere on the side of this Gaussian surface by symmetry? It's all the same, so what can you do with it? Yes, you do. If this is the same anywhere on the surface, we're summing up this contribution all the way on this whole surface.
Oh, we remove it from the.
Yeah, it's a constant, so you can pull that out of the sum. So tell me what this is going to be. If I take a little magnitude of delta A here and sum them all on the side, what do I have to end up with? I just want to know what the sum is.
It's not gonna cancel itself out, right? It's still.
You're just looking at a, this is a magnitude.
Yeah.
So there's no direction in it anymore.
Oh,
You're just looking at a patch of the area.
okay, so then.
So you're taking this little area here patch, and this little area patch, and this little area patch, and this little area patch. You're adding them up on the entire side. So what do you have to end up with?
Rectangle?
It is, but explain the rectangle. Okay, so this will be the area of the side of a cylinder. And Jill claims that that's the area of a rectangle, and I said, good. Now explain what the rectangle is. How do you get a rectangle?
It's like that one picture they always show us, there's like the two lids with the rectangle in the middle, so you like fold it all up. It's probably not very helpful, but that's how I know it's a rectangle.
There's a more easy way. Yes.
I thought we were talking about cylinders.
Yes. So let's actually do, we get to do art. I love doing performance art. I love performance. Okay. So here's my cylinder. Now I want the area of the cylinder. What is this distance here? What is this called? Circumference. What's the circumference? 2 pi. No. This r. 2 pi r. This is your 2 pi r. What do we say this length is here? L. So I'm going to take scissors. I'm going to take scissors and cut it up like this, and then fold this out. If I take my cylinder here, cut it with cylinders, and then let it flat and get a rectangle. What is this length up here? 2 pi r. This is L. So the area is 2 pi RL. This gives me E pi RL. Make sense? Look at this, E times 2 pi RL. All that has to go to charging flows over epsilon naught. Now, if I just say shade in Q enclosed, where is Q enclosed in this picture? If I just say shaded in.
Inside the.
Yeah, this right here. That's my Q enclosed. If I do kind of a side, if I do if I take a saw and cut this in half, I get this. That's my Q enclosed. Does that make sense? Questions? Now, we're going to introduce something. We're going to introduce lambda. So how do we find enclosed? We introduce lambda, which is going to be by definition charged per unit length. Okay, what was charged per unit volume? What symbol? Rho. Rho is charged per unit volume. Lambda is charged per unit length. We're going to get charged per unit area. So let's apply this. Okay. Again, we get to play who's Beard and Grant's tune. Okay, what is a charge enclosed in the Gaussian surface? Q enclosed. Over what length is that distributed? What do we call this length here? L. So this is over L. So our Q enclosed is lambda times L. This goes into here. Look at this, E 2 pi RL equals Q enclosed, which is lambda L over epsilon naught. Well, cancels, that's really good. L. That's really good because L is the length of our imaginary surface, and your answer better not depend on the value of the imaginary surface. Okay. Take this up over here, and then this tells me the electric field is lambda over 2 pi epsilon naught R. So it doesn't fall off as fast. So a point charge goes off as 1 over R squared. This goes off as 1 over R. Yes.
This is just like a, to be sure. So for all of our cases with our 3 geometries,
Yep.
the E is always going to be the same everywhere, right?
Yeah, otherwise you can't do it. And even if you were to take a course in, let's say, the upper level course called advanced, that usually happens. And even if it doesn't happen, it's going to be a case where you can do the integral pretty. Okay, this sum is actually double. Then it'd be a case where you can do it fairly easily.
How would something have unequally distributed E?
You could actually have something where, let's say you have, let's say here's metal. This is a metal shell. I'm going to put in the very center of this a dipole. Okay, we've done dipole. Are we?
So I probably chemistry graphic.
Okay, well, I'll get to that point. The dipole is going to be a positive and negative charge like that. They're separated. What do you think this is going to do? This is actually going to induce a negative charge up here. This one here is going to induce a positive charge. But in a case like that, you no longer have a uniform distribution of charge. It's actually going to vary. So you get that. Well, this problem is a beautiful problem. It's glorious, but it's like a 3-page problem. You have to use some really beautiful methods. Okay, let's try a variation on this. Instead of having just a thin wire, let's say we have a non-conducting infinite cylinder of radius r. So consider a non-conducting uniformly charged infinite cylinder radius r. It's going to look like this. And it goes infinite in that direction as well. Hey, what we're going to do, we're going to find E everywhere. What does that mean?
Oh,
I agree. Where are they? Inside and outside. So if I go here, if that's my center, if I call this R, we'd have two regions here. That'd be R. So find E inside and find E outside. Okay. Okay. Now, how would you know this is a Gauss-Isol problem? An infinite cylinder. It's one of the symmetries. If you ask for the electric field and it's one of the symmetry, the first thing you think is Gauss's law. Okay? Questions? Okay, tell me what to do. You draw your Gaussian surface. And what will this look like? It'll look like, let me make this a little bit. Looks like that. Let's have a length of L. Keep going. How many? Exactly. We have our delta A here. Our delta A here. Our delta A. Let's here. Here that was?
yeah.
Is that? Hopefully it's something. Okay. Okay, proceed. How's the electric field have to go? Yeah, assuming the same thing as before. So in the words of Scooby-Doo, ring, ring, Reggie. So that's our electric field. Now what? How's that integral going to? I'm sorry. For those of you who've had calculus, this is actually an integral. It's actually a two-dimensional integral because it's a surface area. So if I say integral, I really mean the sum. Okay. If I have accidentally put a D in there, it's because I'm used to writing this in terms of physics notation, not like this. So, okay. What does that sum become? How does it compare to the last sum we did? It's the same thing, right? Because what would happen? We'd have this part on the top. We have this part on the bottom. We have this trim on the side. Okay, what do you know about the top and the bottom? They're zero because, yeah, both of these cases here, these are zero since E is perpendicular to delta A. This is zero and this is zero. They don't cancel each other out. They're individually zero. What does this go to? Yeah, this goes to your sum, magnitude V, magnitude of delta A, cosine is zero. What do you do with E? Take it out. Take a little delta A here and sum it up on the whole side. This whole thing is again 2 pi r L. Okay. Then from Gauss's law, this has to equal your charge enclosed or epsilon naught. Okay. So if I had to say color in the charge enclosed, what would you color in? Yeah, it's just this guy here. Tell me how to find that. You need the volume, so you need the rho. Good. Again, what is the definition of rho? Rho is a charge per volume. Okay. Grand sum again. What is the charge enclosed inside our Gaussian surface? Q enclosed. Now you need the volume of a cylinder. What's the area of a volume of a cylinder? I mean, what's the area here? No, exactly. Right. This is our pi r squared. So you take that area times length. So our Q enclosed. Take this over here. This gives me Q enclosed equals rho pi r squared out, and then this goes into here. I love drawing big arrows. Makes sense. Now what? Cancel the L's. One of the R's. And the pi. So we're left with E equals rho R, because the one of the R's here, over 2 epsilon naught. That makes sense? Questions of that? Now what? Do the outer one. Now, if we're careful here, we're not going to have to do any work with the outer one, or minimal work. So I'm going to get a lot of this up here. I'm going to draw the outer one over here. So we come out here to R, we draw our little Gaussian surface. Notice that 3D perspective I'm putting in there. So cool. Like that. Okay. Now, what's going to change for this case here? What do we know about this? It's still going to be this. That doesn't change. Okay. Now, where's the charge enclosed in this case? It's going to be this charge here. All right. I can't go up to here because there's nothing here. Right. The charge is contained inside here. Okay, so how could you easily modify this expression here? What's the only modification you have to do here? It's so close. No. What's your cylinder look like? Your cylinder now is inside here. All right. What's the volume of that cylinder? Almost. It can't be this as if it's little r. I'm saying the charge is going all the way up to here, but it's not. Where does the charge stop? A big R. Yep. Sure.
I don't know how to ask this question, but I feel that the R's in the diagrams are messing up.
Okay, there's two different R's. Okay, the little r is the distance from the center out to the Gaussian surface. This is where we want to find E. The big R is the radius of our cylinder. So this right here, our charge is contained in that guy, but that has our charge. Okay. So when we go over here, right? When we did this guy here, this is our R. Then we do something like this. We call this R. So we need the volume of this guy here, which is the area top, higher square times the length. That's how we got that. Does that make sense? Now what do we have? We don't have this guy. We now have the charge contained in here. We have that charge. Okay. What would that be? Well, that would be the area of this top here. So it's pi big R in times the same length. Does that make sense? These won't be hard once it clicks. When you're first learning this, it feels like you're rolling some kind of tip. What's going on here? Who is flux and why do we need you? And then the charging, and then it can really screw with your head. It's a defined quantity. It tells you how much of something goes out through the surface. Set that part. This is we define it that way. Flux. Flux. So what do we have here? When we do this, we have pretty much the exact same thing. So when we do this, this doesn't change. This right here, this doesn't change either. Okay, there's only one change. The change on this side is that little r has to become big. So you end up with rho pi big R squared. This is now your Q enclosed. Over epsilon rho. That's the only change. So the L's go out, Phys go out, take over 2. This gives us real R squared over 2 epsilon naught R.
How would you know to use the rho one versus the lambda one?
Okay, what was lambda?
The charge of the line.
Okay, this is, so in other words, the wire had no width, so it's just length.
Oh.
This has a diameter of R, or radius of R, capital R. So this is all the volume.
Okay.
That makes sense? So similar to the next test, I'll give you variations on this. That you can play with. Now, the next one, we're not going to do a whole lot. We're not, as far as doing a problem that you don't do a lot of problems. The result, though, we're going to use this result all the time. It's a very practical result. So, what are we up to now? The infinite plane. And so here's a piece of paper like this. Okay. Obviously, I can only draw a finite thing. We're going to assume this is uniformly charged. So I'll put a whole bunch of positive. Again, going back to here. Imagine here's my plane, but again, imagine it's infinite. So I have an infinite piece of paper. I take charge, and I spread charge all over this. The charge is uniformly distributed. And I want to know, what is the electric field? So side view for this. So this is kind of an adjunct view. A side view. Side view, you just see that piece of paper coming out like this. And then positive. Now I want to come out here some distance here. I want to find you here. Okay, how would you know to do Gauss's all of this? It's one of the 3 geometries that you can easily do. Again, Gauss's law is always true. It's one of Maxwell's equations, which entirely summarize electricity and magnetism. But you can only easily use it to find the electric field of those 3 geometries. Okay. So what do we need? This one's gonna be tricky. Always has to be a closed surface. It has to have the same symmetry as this problem. This one's a little, won't be hard once we get it. Well, I have to figure out what kind of surface. So what kind of surface are we going to do? Has to be closed surface.
A rectangle?
Okay, 3-dimensional now. Kind of like a box. What I'm going to do is I'm going to draw a box like this. What do you think about this distance compared to this distance?
Same.
And make it the same. So this is some distance through D, and then this is some distance through D. It's a little hard to draw on this picture here, but I will endeavor to do it. So if I do something like on this one here, what I do is I do something like this. So I have the top part, and then I go back on the bottom part here like this as well. Feel like that. So this is the top part, and this is the bottom part. The area for this guy here on the top. And we call this A. So this is A. Which turns out we can actually use a symbol A for. That's the area, and then this is here it's D. That's it here. And then this is the part below it as well. This is D here. So this is the lower part, and this is the upper part. So to run a little more 3D look to this, be something like this. Be like that. That makes sense? So we can be, so imagine I take a cube and I put it in there. So I have half of the cube up here, then half of the cube down here. Okay. Hey, now one. All right. What's the next step for this? We have to put in the DAs. Okay, how many DAs are we going to have here? I mean, it's delta A's. How many sides? There's 6. We have this guy here. We have this guy here. We have then this guy. That. And this other one like this. We have one in the front and one in the back. Okay. So there'd be 6. We're going to have to. So we're going to do this guy here. This is the total. So you're going to have this guy here. On the top. There's this guy here. On the bottom. This guy here. Right. This guy here on the left. There's this one here in the front. There's this one here in the back. That's 6 turns out. That makes sense? Now, how does the electric field have to look for an infinite plane? Yeah, it's going to be going straight up and down. So the electric field for this is going to be something like this. Let's go over here. That's what it looks like. So what would happen here then? Exactly. The right and the left, the front and the back, the electric fields are all perpendicular to the DA. So if I look here, the electric field is going like this. On all the sides, with the exception of the top and the bottom here, the E is perpendicular to DA. So on right, left, front, and back. E is perpendicular to delta A. So these terms here. This whole expression here for the total. It's the top. What do you know about the top? What do you know about the bottom? Do not product first, but you're right. B, so A, cosine is 0, because there ain't no angle with each other, and then the same thing for the bottom. Right. On the top, this electric field and that delta A are making it 0-degree angle with each other. On the bottom, the delta A goes down, the E goes down, so the angle between these two is 0 as well. Keep going. By symmetry, what can I say about this? Is infinite. Charge is uniformly distributed. So what can I say about the electric field anywhere on the surface? Has to be constant, so I can pull them off. So I would have I needed that picture. Pull them out. So tell me what this is. And tell me what this is. Oh, one other thing. How do I know that this E here equals that E here? How did I set up that box?
This time with the distance, what is on the bottom.
Yeah, so when you set up this box like this is D, and this is D. So the electric field on the top here, magnitude of it, has to equal the magnitude on here. Okay, then what does this guy here become?
Okay, the volume, or the
No.
area.
Which one? If you're starting, well, if you're starting with tiny little areas, it's gonna be the area at the top. So this is your area at the top. This is the area at the bottom. But what do you know about the top and bottom areas? They're the same. So this becomes 2 magnitude of E times the area. And this has to equal the charge enclosed over epsilon naught. So let's draw this. So it was that part and then the part went down. So if I were to say shade in the charge enclosed, where would it be? Is this charge right here? This is our charge enclosed. Okay. So we're going to introduce a new variable. Introduce sigma. What do you think sigma is going to be by definition? Rho is charged for volume. Lambda is charged for length. This is going to be charged for area. Okay. Grant Stone. What is the charge enclosed in the Gaussian surface? Charge enclosed. Over what area is it distributed? What would be this area right here? This is A. So this Q enclosed is sigma times A. And that goes into here.
Why did you say that? It's just
Well,
Epsilon, I'm sorry. Why did you say that was?
oh, because this is a cube or rectangular cylinder, so it has all the dimensions. Any cross section is just A. So this top here is A. So where it's intersecting the object has to be A as well. They put this in here. Those A's cancel, and you get a very odd result. Solve this for E, so that E gives me sigma over 2 epsilon naught. What's odd about this? What does it not depend upon? Yeah, so here's my infinite plane. And so imagine I have an infinite piece of paper, uniformly charged. How does the electric field here compared to here, 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 compared to here? It's a constant. It's a constant due to the fact that this is infinite. It's kind of a fake result. Obviously, you can never have an infinite sheet, but the way you can actually use this expression is, let's say you actually had a charged plate here. If you're toward the center, not too far up, and in this region here, this expression here would actually apply fairly well. So this is independent of distance. Does that make sense? Questions? Now we're going to make something with this. Let's say I have two, so there's an application of this. So this is an infinite sheet. I'm kind of doing an edge view, and here's another one. I'm going to have a battery here. Now here's your little battery. Batteries have a plus sign and they have a negative. And what I'm going to do is I'm going to put a wire here like this. So I'm going to run wire from the positive end here. So this is wire. Into the negative end. Like that. Okay, what does the battery do? Why do you call this in positive and this in negative? This is actually going to be how the electric field goes. So this is going to act like a positive electric field. So how would the electric field have to go for a positive end of the battery? They have to come out. So this electric field would have to come out like this. So that's going to be what this side of the battery does. It sets up an electric field in the wire like this. How to electronegative end? It's going to be going in. E fields go into negative charges. Okay. Now let's say that these are metal sheets. Metal sheets means you're going to have moving charges. If you're a tiny little electron here in that sheet, and you see an electric field like this, what's going to happen? Yeah, the electric field is going to put a force on you. It's going to move you this way toward that positive charge. That little electron is going to come this way, hit this terminal here, then some incomprehensible chemistry that makes absolutely no sense kicks you over to here. So this is weird chemistry. But now the electron ends up over here. Now if the electron's over here, where do you go? Yeah, the force is still going that way. It's going to take you, then move you over on the side here. So now this electron's been moved over to here. Well, if this is lost an electron, what would this now become? It's just lost an electron. This will become negatively charged because it just gained an electron. This will now become positively charged because these things are initially electrically neutral. This will now get a positive charge. But hey, what's going to happen to another electron? The same thing over here. So this gets another electron, and this gets then an equal positive. And this will keep on going on. This is going to become positively charged. This will become negative. So now we have two infinite sheets, one with a positive charge and one with a negative charge. And what we'll do in lab tomorrow is we'll continue with the lecture. We'll continue to go on this. This is going to be called a capacitor. And this is going to be, if you need to have a constant electric field in the lab, and sometimes you do, this is how you're going to make a constant electric field. Okay, enjoy your day.